In this video, we're going to talk about the defining regional convergence of rational causal signals. But before we start, I'm going to freshen up your memory on a few things. First of all, I want to remind you that we're talking about a causal signal. Now, what's a causal signal? We define it as a constant times e to the negative alpha t times the step function. And in the last video, we found the Laplace transform of this causal signal to be that constant over s plus alpha. Now we know that when it comes to finding the Laplace transform of any signal, we need to define two things. And what are those two things? First, we need to give the value of x of s. So we need to find a numerical value for x of s, which we did. In this case, our numerical value is the constant over s plus alpha. And the second thing that we need to define is the region of convergence, which is the region in which our Laplace transform x of s exists. Now, what does it mean for a signal to be rational? Well, it means that our signal is a ratio of two polynomials in S domain. That means that our x of s is not just one, but multiple of these a over s plus alphas. So it's a polynomial, a of s over b of s. Meaning that we can write it in the summation form of multiple constants over multiple s plus alphas. Now I'm going to go ahead and give you an example of this. And let's say our x of s is a constant a1 over s plus 2 plus a2, another constant, over s minus 3. Now, if you notice, again, we still know that our signal was causal, meaning it had multiple components, but both components are causal components, meaning that we have defined what the regional convergence for each component is. So we knew in the last video that if our signal is causal, the value of the Laplace transform is a over s plus alpha, and the regional convergence of the Laplace transform is so that the real part of s is greater than the negative real part of alpha. Now we're going to go ahead and use that. Well, if you only had one component, that would be easy, right? Because we could just say the regional convergence for this total s is in the s domain so that the real part of s is greater than the negative 2, which is the negative real part of alpha. However, here we have two components. So we need to find a region in which both components have in common, in which both components exist, and define that region as the region of convergence of this bigger function that we have. So I'm going to go ahead and draw the regional convergence for each component separately. So I'm going to write the regional convergence for the first component first. So this is my S domain. I have the imaginary axis and I have the real axis. And I already know that this comes from a causal signal by just looking at it. It looks very similar to a over s plus alpha, so I know it comes from a causal signal. And I know the regional convergence is that so that the real part of s is greater than the negative real part of alpha. Where alpha is 2, so the negative real part of alpha is negative 2. And we want the real part of our s to be greater than that. So this is our shaded region in which our first component exists. Now let's go ahead and draw this for the second component as well. Again, this is the S domain. It's the real axis and that's the imaginary axis. Now, again, this comes from a causal signal, and we know that for the causal signal, the R or C is the sigma has to be greater than negative part of alpha. Well, alpha is negative 3, so negative alpha is positive 3, and we want our sigma to be greater than that. And the shaded region is a region of convergence for which the second part exists. Now we need to find a region in common between these two so that we can say in that region not only the first component exists, but the second component exists as well, and so our x of s exists only in that region. Well, I'm going to go ahead and draw this now to make it easier to see. J omega axis and the real part of s. Well, between -2 and 3, the first part exists, but the second part doesn't. However, after +3, the second part exists and the first part exists. So that's the region they have in common. And therefore, the region of convergence for x of s over here is so that sigma has to be greater than +3. Now there's an interesting thing to point out here. I want you to notice that our x of s was a rational causal signal, meaning it had multiple components, but both components were causal. And we know that when it comes to causal signals, if we were to draw in the S domain, the region of convergence is always going to be to the right of our vertical line, because sigma has to be greater than the negative real part of alpha. So once you find the negative real part of alpha, it's going to be to the right of it, of that vertical line, and that is going to be region of convergence. Now, if we have multiple components and we have multiple vertical lines, it's the region of convergence is going to be always, I'm going to emphasize this, always, and this is when we have multiple causal signals. I'm not talking about when we have anti-causal or non-causal components, which we will touch on in the later videos. We're saying that all the components are causal. The region of convergence is going to be always to the rightmost vertical line, which we can see is true over here. The rightmost vertical line was our +3 line, and the total region of convergence turned out to be to the outmost, to the right of the rightmost vertical line, which was over here. I hope you enjoyed this video. Please like and subscribe for more videos in the series to come.